Okay, do you see my slides? Okay, so thanks for the introduction and thanks for the invitation. So my talk is about C-star categories and it's actually meant to be some sort of an introduction to this topic. So don't expect any deep theorems to see here during my talk. And so let me just start with the definition of what a C-star category is. And it's almost what you would expect. So it's almost just a direct generalization of a C-star algebra. So you of course want in your category the morphism spaces to be complex vector spaces, and you want them to be equipped with a norm so that each of these morphism spaces is complete. You of course want submultiplicativity for this norm, and you want a star operation which acts by isometries. And since you want a C-star category and not a Banach category, you also want the C-star identity, which is the third point here on this slide. So up to now, this is exactly what you see as a definition for C-star algebras. And now the fourth point is a bit special, namely that this is something that you have to demand additionally. So you want that F star composed with F is a positive element of the endomorphism C-star algebra. So note that if you have the first 3 points, then each endomorphism space of each object will be a C-star algebra just by these axioms. And in C-star algebras, you can prove that elements of the form x star x are always positive elements, so have positive spectrum. But the problem with C-star categories is that this property does not follow automatically from the first 3 points. So in C-star category, you have to add this as an additional requirement, as a fourth axiom, that F star composed with F is a positive element. And as I have written down here as a remark, this is really indeed needed. I mean, in the sense that there are examples of categories satisfying the first 3 points, but not the fourth. So we know that this is really does not automatically follow from the other points. Okay, but so that's a C-star category. It's basically what you would expect, a direct generalization of C-star algebras. And of course, the main example or the most basic example is that every C-star algebra is a C-star category just with a single object, where the morphism space of this object is just a C-star algebra. Now, other basic examples are, for example, where you use as objects all Hilbert spaces, maybe with a size restriction. And for the morphism spaces, you just take all the bounded linear operators between the 2 Hilbert spaces. Another example is the same set of objects, so Hilbert spaces, but now you only look at compact linear operators for the morphisms. That's actually a wide sub-C-star category of the previous one. And note that in this case, you actually have a non-unitary C-star category, right? Because if the Hilbert space is infinite dimensional, the identity is not a compact operator. So when dealing with C-star categories, you usually deal with non-unitary categories because of this, because many natural examples are actually non-unitary. But for simplicity here in this talk, I will just completely neglect this. So I will never talk about unitality or non-unitality in this talk, just to forget all these technicalities that arise from this. So don't worry about anything with the unit. And generalizing these 2 points, if we have any C-star algebra A given, then you can consider as a C-star category the Hilbert A modules as objects and as morphisms all the bounded adjointable operators between the corresponding 2 objects. And again, similarly as before, you have a wide subcategory where you just consider the compact operators. So these are the main basic examples of C-star categories, and later in my talk, we will see 2 more examples, which really arise in nature, so when you really construct stuff. And of course, you can turn C-star categories into a category themselves. So first, you of course do the natural thing. You define a C-star functor to be a functor which is linear and preserves the adjoint. And then you have C-star cat is the category with objects, the C-star categories, and morphisms, the C-star functors. So if you're wondering here in this definition of a C-star functor where the multiplicativity property went, right? So usually you of course want to generalize star homomorphisms from C star algebras, and they are of course multiplicative. And the word multiplicative does not occur here. So if you're wondering where this went, it's subsumed in the word functor, right? Because in a C star category, the composition of errors is the multiplication. So therefore saying functor is already the multiplicative property of these things. Examples are, of course, just the inclusion of this category where you consider only the compact operators into the whole category where you consider all bounded adjointable operators. That's a C-star functor. And you, of course, have, just considering a C-star algebra as a C-star category with a single object. It's also just a fully faithful functor. Okay, before I go on with why do we want to consider C-star categories, do you have up to now any questions about the basics here, about the definition? Nobody, perfect. So, yes. So why do we consider C-star categories at all? So why do we want to generalize from C-star algebras to C-star categories? And especially, as you see here in the first sentence, why do we want to extend the definition of K-theory or KK theory from C-star algebras to C-star categories?
Actually, we
And
did end up
yes,
getting a question.
yes,
Any size conditions in the definition of a C-star category?
where you usually use some sort of size restriction,
Okay.
whichever suits your context. Yes, so the reason why we want to generalize to C-star categories is that sometimes you encounter problems when you want to define something just using C-star algebras. Usually these are sort of functoriality problems. And sometimes you can solve these functoriality problems by passing to a suitable C-star category as an intermediate step. So I will give you now two examples where this happens. So the first example is in my own work in coarse geometry. Don't worry, I don't assume any knowledge of you about coarse geometry because I will neglect all the words that you have to put here. So this is just a very basic idea of what's going on when you want to define coarse K homology. So say you have a proper metric space X and you want to define coarse K homology of X. So what you classically do is you choose a separable Hilbert space H and a suitable star representation of the C0 functions of X on this Hilbert space. I don't want to say what suitable means here. It doesn't matter. And once you have fixed this choice of a Hilbert space and such a representation, then you define a certain C-star algebra, which is by definition a sub-C-star algebra of the bounded operators on this Hilbert space. So how you define the C-star algebra is you basically say you consider all the operators which are locally compact and finite propagation, and you close up an operator norm. Again, for this talk, it does not matter what these two terms mean. It's just fine to know that it's a certain sub-C-star algebra of the bounded operators on this fixed Hilbert space that we have chosen. And once you have the C-star algebra, you then say, well, the coarse K homology of X should be the K theory of this thing. And then you, of course, want functoriality. So assume you have two such metric spaces X and Y and a suitable map between them. So something like Lipschitz and proper would do the job. And well, you want to define a map from the K homology, coarse K homology of X to the one of Y. So what you do is, so you have these fixed choices of Hilbert spaces and representations for X and for Y. And then you have to choose a suitable isometry from one Hilbert space to the other Hilbert space. And then conjugation by this isometry will give you a map on the row algebras, on these C-star algebras that you use to define functoriality. And you see the problems here. So we have basically two choices involved, right? So first, for every such metric space X, we choose classically a Hilbert space. And for functoriality, we have to choose an isometry. And everything here is fine on K-theory groups, because what you can show is that any two choices that you can do here are related by conjugation by unitary, for example. So on K-theory groups, everything is fine what you do here. But if you want to make the spectrum valued, then you get a problem, because then the choices actually might matter. So here you have really an issue arising from the fact that you're forced to make choices. And as I said, the solution is to go to a suitable C-star category. So instead of defining a C-star algebra, we define a suitable C-star category where everything becomes canonical without any choices. So how do we do this? And it's basically a dumb idea, namely in the sense that you consider everything at once. So all the choices that you can do, you just consider them all. Meaning that you now define a C-star category whose objects are all these pairs of Hilbert space and representation that you can choose. So you don't choose one, you just consider them all just as the objects. And the morphisms in your C-star category are then just the corresponding ones that you use in the row algebra. So you again say the words locally compact and finite propagation and so on. And so you get a C-star category. And the advantage of this is, well, firstly, we don't have to make a choice of a Hilbert space anymore. And secondly, functoriality is now completely canonical. Because if we have again such a map F between two matrix spaces, you can canonically define a C-star functor from the row category of X to the row category of Y. So it's just canonically given this map. So again, there's no choice of it. So before we had to choose an isometry, here we don't have to choose any isometry at all. And you're done. And then you define the cos K homology of X just as the K-theory spectrum you can do now of the C-star category. Once you have suitably extended K-theory from C-star algebras to C-star categories. So that was the first example. The second example, that's probably something that you might have already seen here in this workshop. It's the general construction of assembly maps due to Davis and Luc. So what they have done is, so given any functor from the orbit category of G to spectra gives rise to an assembly map. That's what they have defined then. So so basically it's an assembly map machine. You throw in such a functor and this machine then spills out an assembly map. And if you plug in correspondingly algebraic K-theory, L-theory, or topological K-theory, then you get the Farrell-Jones assembly maps or the Baum-Kohn assembly map. But here in this construction, you get the same problem that you have to make choices in order to get functoriality. And again, you can solve it by passing to a C-star category. So for this, we recall that the orbit category of a group G has as objects all the homogeneous G spaces, G mod H, and as morphisms just all the G maps between such things. Now to get the Baum-Kohn assembly map, we would like to do the following. To such an object, G mod H, we would like to assign the spectrum K-theory of the reduced group C-star algebra of H. And to a morphism from G mod H to G mod K, we would like to do the following. So note that such a morphism is always given by right multiplication with a certain element small g. So we fix such a g, which gives this morphism by right multiplication, and then we can define the map CG, which is basically conjugation by this element g. And this should act on the reduced group C-star algebras and give us the corresponding morphism. Let us here for the start just ignore the problem that reduced group C-star algebras are in general not functorial for arbitrary group homomorphisms. That's a different issue. But the thing here is, in order to define it like this here, you are again forced to make a choice. Namely, so I said every morphism from G mod H to G mod K is given by right multiplication with a group element small g. But the thing is that this group element small g is not unique, because you can replace g by g times k for every element k in the group k, in the subgroup k. And the resulting maps that you use on the K-theory of the reduced group C-star algebras, so the conjugation maps, they will differ from each other by conjugation by this unitary defined by this group element K on the reduced group C-star algebras. And so again, you have the problem that, well, if you do it just on K-theory groups, everything is fine because conjugation by unitaries acts trivially. But if you do it spectrum valued, as you need it here for this Davis-Luke assembly map machine, then you have the problem that conjugation does not necessarily act trivially on the spectrum. And so again, you have the problem that it's bad for you to make this choice of this group element G. And the solution here is again to pass suitably to a C-star category. And the C-star category, you define it like this. So it's basically you define a functor from the orbit category to C-star categories, and then you post-compose this with the K-theory functor that you have extended from C-star algebras to C-star categories. Okay, how is this functor to C-star categories defined? So an object G mod H from the orbit category, you map it to the C-star category whose set of objects is G mod H again. And the morphism space for two cosets in the C-star category is generated by such group elements L with this property. So what does generated mean? Well, it's basically, you have to take all these group elements L, then you span a complex vector space with them, and then you have to put a suitable C-star norm on on this stuff. For this talk, it's not relevant how you concretely do this, but just it's basically every element is a generator of the resulting morphism space. And yeah, so we have defined the functor on objects, and on morphisms, you do the following. So you have a morphism from G mod H to G mod K, and you map it to the C-star functor, which is this morphism itself on the objects, and it's the identity on the generators. So meaning that this group element L makes sense as a generator both in the domain and in the target of this morphism. Yes, and once you have this, you then apply the K-theory of C-star categories to this, and you have your functor on the orbit category that you can plug in into this assembly map machine of Davis and Zook to get the Baum-Cohn assembly map. Yes. I will tell you in this talk, of course, how to extend K-theory to C-star categories. But are there up to now any questions about these two examples? No. Okay. So how do we extend K-theory and also KK theory along this inclusion from C-star algebras to C-star categories? And the idea, which I will explain to you, is due to Michael Joachim, and this is actually, as you will see, quite easy to state. Namely, you have this inclusion. C-star algebras go to C-star categories, and the thing is, this functor, it has a left adjoint from C-star categories to C-star algebras in this case then, which is called AF in the paper by Michael Joachim. And you just use this left adjoint to extend K-theory or KK theory from C-star algebras to C-star categories. Right, so you just have a C-star category, so you apply this left adjoint to it, you end up with a C-star algebra, and then you can take the K-theory spectrum, for example, of the C-star algebra. Or you can compose further to the KK category if you want to do KK theory. So that's just the whole idea. You just apply this left adjoint. Of course, this left adjoint has a concrete formula. I will explain this to you later in this talk, how this left adjoint AF concretely looks like. Okay, now to the second half of my talk. So it's basically about now unitary equivalences. So let me maybe go back to the previous two examples on my slides. So let me go back to the row algebra stuff. Okay, so here I said, well, we have to make choices classically. we have firstly to make a choice of the Hilbert space and representation, and then secondly, we have to make a choice of an isometry to get functoriality. And then I said that classically this is no problem. So on K-theory groups, this is no problem because two different choices of Hilbert spaces and representations will be related to each other by conjugation by a unitary. So unitary from one Hilbert space to the other Hilbert space. And also two possible choices of suitable isometries for the functoriality will be related to each other, again by conjugation by an isometry. And we know that on K-theory groups, such conjugations act trivially on the K-theory groups. But on spectra, they do not act trivially necessarily. But of course, what we can show is that on the K-theory spectrum, this action is an equivalence. And this is something that you can show for K-theory and for KK theory. And I want to explain to you now how to show this just using the axioms. And you have the same thing happening here in this example. So recall that here in this example, so where was the choice? It was for the morphisms, where we said that every morphism between two such homogeneous G spaces is given by right multiplication by a group element small g. And two different choices of such group elements small g, they differ from each other by conjugation by a group element acting on the reduced group C-star algebra. And this group element will be a unitary, so it's basically an inner conjugation because this group element corresponds to a unitary in this reduced group C-star algebra. It's a generator in it. So again, here two different choices differ by conjugation by a unitary. Now, if you recall from, for example, Uli's talks here in the workshop, the axiomatic definition of KK theory. So the axioms were something like homotopy, invariance, stability with respect to tensor with the compact operators, and exactness. Now, none of these axioms talks about conjugation by unitaries, right? None of these axioms talks about unitaries at all. But still, using these axioms, we can show that conjugation by a unitary is an equivalence. And we can actually even show this for C-star categories, so for the extension of K-theory and KK theory to C-star categories. And that's what I want to basically prove to you now. So therefore, first, I have to define what in a C-star category a unitary equivalence is. Now assume we have two C-star categories, C and D, and we have two C-star functors, F and G, from C to D. Now we call them unitarily equivalent if there's a natural isomorphism from F to G, which just acts unitarily. So meaning that in this square that you write down to define what a natural isomorphism is or what a natural transformation is, in the square you just demand the corresponding vertical arrows here to be unitaries. Yes, and so these are unitarily equivalent functors in between two C-star categories. Now, if you want to, you can use unitary equivalences to actually turn C-star cat into a 2-1 category, right? Just as using two morphisms, the unitary equivalences. And then you can do interesting stuff with this, for example, invert unitary equivalences, as Uli did in one of his papers, and then investigate the resulting infinity category and whatever. But here in this talk, we want to prove this proposition. So assume that we have some sort of homology theory for C-star algebras. So we have a functor from C-star algebras to an infinity category S, and this functor should be matrix stable and homotopy invariant. So for example, it could be K-theory, where you map to spectra, or it could be KK theory, where you map to the KK category. And the proposition states that matrix stability and homotopy invariance is enough in order to prove that the extension of this functor to C-star categories sends unitarily equivalent C-star functors to equivalent morphisms in S. which coincide in the homotopy category of S. Okay, so how to prove this? So for this, of course, we have to know how this functor AF concretely looks like, because up to now I just said it's the left adjoint of the inclusion functor of C-star algebras to C-star categories. Okay, how is AF now concretely defined? So you have a C-star category C. So what you first do is you consider the star algebra, which is freely generated by all the morphisms in this category C. And on this thing, you then form the quotient by an equivalence relation, which just reflects the sum, the composition, and the star operation, which you have in the category C. I mean, what do I mean with this? So for example, assume you have a morphism F and a morphism G in the C-star category C, which are composable. Then in the star algebra freely generated by the morphisms, the generator corresponding to F multiplied with the generator corresponding to G, it's a different element than the generator corresponding to F composed with G. And so we have to form this equivalence relation and then the quotient along this equivalence relation, which identifies this again, so that you really get the composition that you have in C also in this star algebra. And once you have this, you just put the maximal C-star norm on this thing, and completing this gives you a C-star algebra, which is then AF of C. So for later reference in the next proof, let us denote generators in this AF of C, C-star algebra, just by parenthesis phi. So phi is a morphism in the category C, and parenthesis phi will denote a generator corresponding to this morphism in this C-star algebra. Okay, now let us just prove this proposition. So let f and g be these unitarily equivalent C-star functors, and we want to show that A composed with AF of F is equivalent to E composed with AF of F is equivalent to E composed with AF of G. And the idea to do this is just basically to somehow elaborate on the rotation trick that one uses for K-theory groups. So if you maybe recall how you prove for K-theory, for the group-valued K-theory, that conjugation by unitaries acts trivially, then it's a certain rotation trick in 2x2 matrices. And what you do here is basically the same thing, just you have to be a bit more cautious with the formula that you write down.
Wait, a quick
Okay, now let
question.
eta, yes.
So now you need your C-star category to be small. That's a question in chat.
Um, what does small mean?
I mean, I'm guessing in the set theoretic sense. Ah, thanks, Uli.
What did Uli post?
Uh, AFC is in the next universe. So just pass into some higher growth indic universe, then it's fine.
Okay. Thanks, Uli. Okay, let us denote this unitary equivalence by eta, and let us denote the components of it by eta c. So small c is an object in the C-star category C, and we have here all the components eta c of this unitary equivalence. And let us also look at the morphism phi and the corresponding generator in this AF C-star algebra. And now we want to write down a homotopy in 2x2 matrices in AF of D between the diagonal matrix 0 in the upper left corner and f of phi in the lower right corner, and diagonal matrix g of phi in the upper left corner and 0 in the lower right corner. And it's basically this formula that you see here. So you just multiply all these 2 by 2 matrices with each other. UT are these rotation homotopies with sine and cosine. And if you just evaluate this stuff at the beginning and at the end of your time interval, then you see that at 0, it's the first diagonal matrix that you want, and at the other end of the time, it's the other diagonal matrix that you want. So it's a continuous homotopy in 2 by 2 matrices between F and G. Now, okay, F and G, they are now in different corners of the 2 by 2 matrices, but then you can just afterwards do again a rotation to put it into the other corner, and then you use matrix stability in order to basically say, well, 2 by 2 matrices doesn't matter, it's fine. And you're basically done. So you know that they are homotopic to each other, so that just proves the proposition. Well, the thing is now, okay, we have written down this formula now in just one single generator phi. Now we apply these homotopies to all the generators simultaneously. So for this, you have to check that, well, so what was the definition of AF? First, you formed the free algebra on these generators. So that's fine just to do with the generators whatever you want, because it's a free algebra on these generators, so you can just change the generators as you want. It's compatible with everything. But then you did this quotient by this equivalence relation, and especially you had this equivalence relation which takes your composition in the C-star category C and puts this into your AF algebra. And for this, you have to check that your homotopies that you have here actually respect this composition. And yeah, you can do this. This is just a direct computation that it's just compatible with the multiplicative relation that you have here. And so therefore, these homotopies, they descend to really the AF algebra. And you're done. And this proves the proposition. Any questions up to now? No. Perfect. Well, I have 60 minutes time, right? Okay. But the thing is that I noticed that I went far too fast.
Perfectly fine.
Okay. Yeah, I mean, then we have more time for discussion or questions now. So let's thank Alexander. Are there any questions? Maybe Uli?
No. I think
You just unmuted yourself, sorry.
no.
I had the same amount of slides as in another talk, but this other talk was 60 minutes. So therefore, I thought this will be also roughly 60 minutes.
So, I mean, one question is, I mean, I've discussed this with Uli, but so what kind of exactness properties does K-theory for unital C-star categories have? So if you don't want to talk about ideal inclusions, is there any nice way to formulate exactness on a level of categories?
But I mean, if you want to say something about exactness, I mean, you have to talk about ideal inclusions somehow.
Probably somehow. I mean, the question is, of course, motivated by trying to make the story for additive categories and C-star categories more parallel. So, and in the additive context, you can phrase some versions of exactness, at least just using unital categories, no?
But I've never thought about this in this way. Because for me, so for all the stuff that I was doing, basically the naive definition that you would do by writing down what a short exit sequence in C-star categories is, this suffices.
Sure, thanks. Okay, so if there are no more questions right now, then let's maybe stop the recording.